Hello, my name is Stefan van Beek and I'm an application engineer with the MathWorks. Welcome to this webinar using HDL Coder and HDL Verifier for FPGA and ASIC designs. Many companies today use MATLAB and Simulink to design their DSP algorithms, but the step to implement these algorithms on FPGAs and ASICs is often seen as a challenging step. In this webinar I will discuss best practices to overcome these challenges and how to efficiently map these algorithms to FPGAs and ASICs. Best practice 1 is using modeling and simulation to optimize at the system level using Simulink and Simulink fixed point. Here we will show you how you can use the Simulink fixed point tool to reduce the word length of your fixed point data types to have more area efficient and more power efficient implementations. Best practice 2. Automatically generate readable and traceable HDL code using HDL Coder. Here we will show you how HDL Coder can be used to automatically generate HDL code to speed up the process of getting to FPGA and ASIC implementations. But in addition we will also discuss techniques which can be used to have more area efficient or more speed efficient implementations. Best practice 3. Reusing system level test benches for HDL verification using HDL Verifier. Here we will show you how HDL Verifier can be used to significantly reduce the time needed for HDL verification. And the last best practice 4, enable regression testing with FPGA in the loop using HDL Verifier. And here we will be using FPGA acceleration so we can process larger data sets to better test our algorithms. So one example of a customer who is already using these best practices is Semtech. And as a result of using these best practices, they were able to get to prototypes 50% faster. They were able to significantly cut down verification time from weeks to days. And as a result of the fact that they were able to get to prototypes much faster, they were having better optimized, better performing designs. And after prototyping they actually used the same code also for their ASIC implementations. So let's have a look at the first best practice in more detail, using modeling and simulation to optimize at the system level, and in this particular case fixed point conversion and optimization by using Simulink and Simulink fixed point. Essentially the fixed point tool will assist you with converting floating point models to optimized fixed point models by automatically tracking signal ranges, which also includes intermediate quantities such as accumulators, and with that make a recommendation for word or fraction length. But in addition, because we are having floating point and fixed point models in the same environment, we will now be able to compare the impact of fixed point quantization and to quantify the error introduced by fixed point conversion. So let's now go to MATLAB and Simulink and look at an example of this. To illustrate all best practices, we have chosen an audio equalizer as an example. And like any design, you always start off by defining the requirements relevant for that particular design. And in my case, these requirements are captured in this Excel document. And so they describe things like which effects the audio equalizer needs to be able to handle, filter specifications for my left and right filter banks, what kind of filter type for instance. But one requirement I'm particularly interested in is fixed point quantization. And in this case, the word length should be optimized for my FPGA target, which essentially means that I want to reduce the word length as much as possible to be more area efficient and to be more power efficient. The fewer the bits, the better it is in that sense. Now, in order to know which part of my model is relevant for this particular requirement, I click on this icon and it will automatically highlight that subsystem in my system to which this requirement applies to. And I have this traceability because I created a link between that particular requirement and this particular subsystem. So this is a traceability from requirements document to my filter subsystem, but I can also easily go back like this, and it will highlight that particular requirement in my requirements document. Now, so it seems that the filter subsystem is a part of my design which I need to further optimize for my fixed point data types. And if you just drill down into this subsystem, you will see that we have a left and right filter bank, and where in the end this is my filter which performs the functionality of the 10 filter banks for the left audio channel in this case. Now, to optimize that part of my system for instance for word length, I'm going to use Simulink fixed point to do this. So let's right click on this subsystem to fire up the fixed point tool. And for the fixed point tool, there are a few things important to configure it. So the first thing is I need to have a certain fixed point instrumentation mode, and in this case I'm interested in capturing minimum values, maximum values, but also overflow. So if by any chance my fixed point data types are introducing overflows, then that is obviously also something I want to know. And I need to override my data types with doubles. So I already have a first guess for fixed point data types, but I'm now going to switch it to double, so the model will behave as if it is having double data types in order to capture the true dynamic range. So let's run simulate, and you will see that for every block it will give me min values and max values, indicating the range for that particular place in my model. Now, based on this range, I can now ask for a proposal, and I can ask for a proposal for fraction length. Assume the word length is perfect, but I want to scale the fraction length to grow or to become smaller depending on dynamic range. Or I can assume that the fraction length is perfect, and I can just scale the word length, and that is particularly now the mode for which I want to use the fixed point tool now. So after I've changed this, I can now ask for a word length proposal. So depending on the fraction length and dynamic range, it can now calculate which word length is needed for or can be used for that particular situation. And as you might see here, that there are a few places where it now proposes a different word length. For instance, in my original design I've used a 32-bit data type, and it says that it can be reduced to 28 bits, which saves me 4 bits. And there are more places where we can significantly reduce the number of bits, which in the end will help me to be more area and power efficient. Now, I can still propose, change the proposal to a different data type, or I can choose to either accept or not accept any proposal. So I still have all flexibility to change the proposal for of the fixed point tool. In addition, I can also choose to have safety margins. So let's say that for the simulation min-max value, I want to add a 40% margin, just to be on the safe side, to make sure that I'm really covering the dynamic range. And I can ask for a new proposal. So on top of the captured dynamic range, it will now add a 40% safety margin. Now let's say that that really makes me happy, and after that I can simply say, well, just apply accepted word lengths. And if I will now go back to data type override, setting this back to use local settings, I can run a verification step to make sure that I haven't introduced any overflows as a result of the fixed point of the changing of the word length. And as you can see, at this point there are no overflows, so it seems that this word length works well, so it's more efficient in terms because I need fewer bits, and it still doesn't cause any overflows. So this is a way, something you can do to have more efficient fixed point data types, and the fixed point tool is a tool which can help you with performing this kind of analysis. So let's go back to the PowerPoint presentation and discuss the next best practice. Best practice 2 is automatically generating readable, traceable HDL code for FPGA and ASIC designs. And while our example today mainly focuses on a workflow which starts from Simulink to HDL, we can also provide you with a workflow which can take you from MATLAB to HDL. So let's see how this best practice can be applied to our audio equalizer and how we can apply speed and area optimizations to that model. Okay, so let's go to the next model to illustrate how the second best practice can be applied to the audio equalizer model. So this is exactly the same model as we had before, with that difference is that now we have optimized our fixed point data types, and in order to generate HDL code, I am going to start up the HDL Workflow Advisor. The HDL Workflow Advisor essentially is a workflow tool which guides me through all steps needed for HDL code generation. Now the first step in this workflow is to choose from a target, and a target in this case means a target workflow. So the HDL Workflow Advisor facilitates different workflows, and the one which I am interested right now is generic ASIC FPGA in order to perform design space exploration. The other workflows we will discuss in more detail later on in this webinar. In order to perform design space exploration, I also need to choose the synthesis tool required for my specific FPGA target, and right now I'm choosing for Xilinx ISE because I want to target a Vertex 6 device, for instance this one. So I can just simply run this task. Perform all steps required for preparing the model for HDL code generation. So essentially it will perform checks to see whether my model is compatible for HDL code generation. Then in the third step, HDL code generation, I can configure HDL Coder how HDL code should be generated. For instance, for what language, which reports do I want, do I want to have an asynchronous or a synchronous reset? So let's choose for a synchronous reset, and then I can simply generate code. And it will not only generate code, it will also generate for me a report which I can use to analyze the generated code. And one thing you may want to look into is how many resources are used in this particular implementation. So how many multipliers, how many adders, subtractors, how many registers, how many RAMs, and how many multiplexers. So this is the summary view, but I can also just drill down into, for instance, every subsystem, and already at this point I have a link where this particular multiplier is used. For instance, if I just click on that link, it will take me to that to the particular place in the model which where that particular resource is used. But I can also further simply just click on any of these generated source files and have a closer look at the generated HDL code. And here also I have a traceability link between the generated code, for instance, where this and the model. If I want to know where this particular code for this unit delay comes from, I just can click on the link. It will take me to that particular place in the model where that code comes from. Well, this is a traceability. This is a bidirectional link, so I can just trace from the code to the model and back to the code. So I can simply say navigate back to the code, and it will take me to that particular unit delay. Now, one other thing you may have noticed is that we had requirements linked to our model, and because of that, we have also the requirements listed in our generated HDL code, which extends the requirements traceability all the way down to the code. And it's not just dumb text, it is actually also a link which I can simply just click on, and it will highlight that particular requirement in the requirements document. So as you can see, the traceability goes from requirements, model, code, and vice versa. So I would say that this is particularly nice when it comes to understanding how code has been generated from a particular model. And we provide this kind of traceability all the way down from Simulink, MATLAB, and Stateflow. Okay, so now I have generated code for the first time, and there are a few things which I may want to optimize. For instance, I may want to optimize an area, but let's first explore how am I doing in terms of timing. So in order to do that, I want to run FPGA synthesis and analyze the timing results as a result of that. So the first step here is to actually create an FPGA project. So if I would have any black boxes, I could include additional source files here, but I do not have any black boxes here, so I can simply now run this task, and this will create for me an FPGA project by using Xilinx ISE under the hood, of course. Okay, so we have now created a project using Xilinx ISE. Let's now run the remaining steps: logic synthesis, mapping, and place and route. And in this particular case, I've chosen to skip place and route because at this point I only want to look at the timing the pre-route timing information given by the mapping phase. So let's run to this step. Okay, so now we have performed all steps. Let's now annotate the model with the synthesis result. And as I only performed mapping, I only have pre-route timing information. So if I just run this task, it will read the timing report from Xilinx ISE, and it will annotate the model with that information. So if I just drill down, then I can see that the critical path starts here with this unit delay. And as you can see, we annotate the path with the cumulative delay information. It goes like here, goes through this sum of elements block, through the game block, to the output, and it ends here at this unit delay. Now, if I want to optimize, so let's reset the highlighting. So if I just want to optimize this part of my system, I may want to add some pipelining stages, for instance, to the output of this sum of elements block. So I just go to the HDL block properties, specify that I want to have 5 output pipeline stages, that I want to have a tree structure. But particularly, I also want to make sure that, for instance, this product block also gets an output pipeline register. So to make sure that I will get one, I can actually add a constraint to the retiming process by specifying a constraint output pipeline of 1 to that particular subsystem. And if I just go up at the subsystem level, I just want to make sure that also at the model level retiming is performed. So I just enable distributed pipelining. So let's now go back to the code generation, just run this task. It will regenerate code, and in this case we will have a closer look at the distributed pipelining report. Now you can see here that we actually had a constrained output pipeline register, output pipeline for that particular product block of 1, and the status here says it passed. So it was able to satisfy that requirement. Here I will have more details in terms of pipeline distribution. For instance, before I had 9 registers, and after distributed pipelining I have 22 registers, obviously because I merged them, pushed them into branches and so forth, which increases the number of registers, of course. But if I want to make sure, if I want to see how the pipeline distribution actually has happened, we have automatically generated a model after the transformation. So I just click on this link. It will give me a new automatically generated model. So it has a prefix of GM, which stands for generated model. And if I just drill down into the filter bank, you see that we actually added pipelining stages into the right filter bank. And you may notice that we actually added compensation delays for the left filter bank to make sure that the delays and that the total number of delays added to the system is equal for both paths through the system. But if I just drill down into this filter bank, you actually see that we have pushed all the pipelining stages into the sum of elements tree structure to make sure that that is well pipelined. And you also see that the product block here also has an output pipeline register. It has a different color, green, indicating that that particular pipeline register is there as a result of constrained retiming. Now, the thing about this model is that the operating sampling rate is low, so it doesn't really need any pipelining to. So there are really no. I mean, achieving speed here is not the main issue. So I just remove the pipelining stages right now. But area is more of a concern. I just want to, so as we already noticed in the first run, we were using a lot of multipliers, and this is something I want to reduce one way or the other. Now, because this design actually runs at a relatively low rate compared to my clock speed, there is some opportunity there to perform resource sharing, and more specifically in the filter block. Remember, this is by far the part of my system which consumes the highest number of multipliers and adders. And for already quite a few releases, HDL Coder supports the concepts of sharing and streaming. Sharing means that I can share multiplier resources or identical subsystems. Streaming, on the other hand, is like multi-channelization. It works on vectorized subsystems, which I happen to have here. So here I have a subsystem which I feed with a vector of 10. So I could specify a streaming factor of 10 here. And let's do the same also for the other filter subsystem. So let's say that I also want to specify a streaming factor of 10 here. And remember, in the first run we needed at least 82 multipliers. So let's see how we are doing now. So let's rerun this task. And you see that how easy it was to push in, to perform to insert the pipelining stages, to perform the model retiming, and it is just as easy to also specify resource sharing constructs like sharing and streaming. Now I go to the streaming and sharing menu, and it tells me that for both cases, for both filter subsystems, I specified a streaming factor of 10 where streaming actually has been successful, and it also gives me a list of other possible streaming factors. Now, as you see, as a result of streaming, we actually have introduced additional delay, which is not surprisingly, but that is a fact of this type of optimization. And we are actually reporting how much delay has been added because of any optimization actually. Now, where we had the with the distributed pipelining, we had a model where we could see the way how the pipelining stages were distributed. We actually also have a model which we would call a validation model. And this validation model to me serves two purposes. One is it gives me a graphical view on the architecture which we have implemented. So if I just drill down into this subsystem, this is the way how this is the architecture which we have implemented. And remember, we haven't changed the structure of the original model. We simply configured it to perform streaming, for instance. And you may notice here that we actually have increased the internal delays of this particular part of the model to be able to maintain the internal state of 10 filters. So in Z-1 becomes a Z-10. And we have also automatically introduced serialization and deserialization components, which translate a vector of 10 to a serial stream of samples running at a 10 times faster rate. So if I would simply look at the sample time legend, you will see that there is a 10:1 ratio between the red and the green sampling rate. Now this is one purpose, which is, to me, it's very nice to see what has happened, what has been implemented in terms of hardware architectures, but it's also a validation model. So if I just drill down here, we are actually comparing the simulation results of the implementation architecture with the original design, and that of course should not show any differences. So if I just enable all scopes and I just run the simulate button, this will tell me that all simulation results of both the implementation model as well as my original model are the same. So this is a nice way of quickly validating whether the architecture which we have chosen is still doing the right thing, and this is a quick way of ensuring that that has happened. Now if I just look at the resource utilization report, and that is actually the more interesting bit, we saw that in the first run we needed at least 82 multipliers. That has been reduced to 10 multipliers. We also needed a significant amount of adders. Again, that has been reduced a lot. And you actually also can see that some of the large integer delays which have been introduced, we were able to map them to RAM blocks. Again, whether this happens or not, it is configurable, but in this case the model has been configured to actually map those parts of my system also to block RAM. So let's go back to the PowerPoint presentation. Okay, so we have seen in the first part of the demo where we were able to use the HDL Workflow Advisor to generate HDL code, where we had full traceability between requirements, model and generated code, and where we could also use the traceability between the code and the model to analyze whether we liked the generated code, and where we didn't like any particular part of the code, we had a traceability link back to the model, where we potentially could change something in the model and have a new HDL code generation run. We also looked at ways how we could improve speed, for instance by using pipelining, and here we used the critical path highlighting as a way to understand which parts of my design were critical. And then we made use of some of the advanced pipelining options for pipeline distribution, automatic delay compensation, and additionally where we could also use constrained retiming to influence the model retiming. And last part of the demo was to actually use some of the area optimizations like streaming to have more area efficient implementations, where we actually, as I said, used streaming. we had automatically generated validation models to gain confidence that that what has been created actually still performs identical to my original model, and where the resource utilization reports provide early feedback on resource utilization. And this also showed that the streaming actually had a lot of impact in terms of resource reduction. Okay, so up until now we have focused a lot on HDL Coder and implementation, but obviously there is also a verification side to the whole workflow. But if you look at the verification landscape as such, and then there are different tests being performed at different levels of abstraction. For instance, at the model level, an important aspect is I need to make sure that my model meets my requirements. For that reason, we actually create the links between the requirements and the model to ensure that a particular requirement is implemented in a particular part of my system. I need to perform functional verification because in the end my model needs to perform the correct functional behavior. If I go through different refinement steps, I need to make sure that after every refinement my model is still equivalent to the previous steps in a sense, or stay within a certain defined error tolerance. Coverage analysis, so how well have I tested my model? Again, it might be an important aspect. Property proving, so you may want to formally prove that certain things can happen or certain things cannot happen. Or ultimately you may want to generate TLM components and take that to System C verification frameworks, for instance. If you just go one level deeper, HDL, there are still some of these tests which are similar. I still need to make sure that my HDL code satisfies my requirements. I need to make sure that my HDL code performs identical or stays within a certain error tolerance as opposed to the behavior of my model. I may want to perform code coverage analysis, assertions, in a similar way as you would be performing property proving, for instance. And the last level, at the FPGA level, I may need to make sure, again, that the algorithm performs equivalent compared to my reference model. I may want to perform regression testing, send higher, larger data sets through my system, through the algorithm on my FPGA, to gain higher levels of confidence that what has been implemented is really performing as it should be. Timing analysis, am I meeting my timing objectives? On target prototyping, so at some point I may want to deploy the algorithm standalone on an FPGA board. So these are just, I think, a few examples of verification steps you may want to perform at different levels of abstraction. The problem here is that test benches are typically not shareable between different levels of abstraction. So I have a test bench in my modeling environment in Simulink, but can I reuse it for my HDL verification, or can I reuse it for my FPGA verification? Well, that is what we are going to explore with the third best practice, how we can reuse the system level test bench for HDL verification. And more specifically, we're going to look at HDL co-simulation techniques to verify the HDL code, which ultimately will allow me to reuse this test bench also for equivalence checking, which in the end, if I would want to, would allow me to integrate with HDL code coverage analysis, provides me with a way for very flexible test bench creation. So if the test bench itself has a closed loop, which is not a problem. If the test bench itself has multi-domain components, so I might have analog components that can easily be simulated by using HDL co-simulation. Obviously this also works with handwritten code, and ultimately this allows me to integrate with ModelSim or QuestaSim or Cadence Incisive. Okay, so let's see how the audio equalizer demo can be used to perform HDL code simulation in order to verify the generated HDL code. So we're going to use the HDL Workflow Advisor also for this one. So let's start up the HDL Workflow Advisor. And right now here I not only selected to have RTL code, I also selected the option to generate a code simulation model, which requires obviously HDL Verifier, and the result will be a code simulation model for use with Mental Graphics ModelSim, but we could also generate a code simulation model for Cadence Incisive. So let's run to this step. Now, in addition, I also could have chosen to have to generate an RTL test bench, which essentially is a self-checking HDL test bench, which I can run in any available HDL simulator, and it will be simply a pass or fail kind of test bench. Okay, we have generated our code. Okay, so what we have now is a model, an HDL code simulation model, very similar to the validation model we have seen before. We have our reference model, we have our HDL code simulation block, which in this particular case establishes a link with Mental Graphics ModelSim. The model also has been instrumented by comparing the output of my reference model with the output of ModelSim. So let's close this one. I want to see the right and left audio channel. Just double click on the blue block to start up ModelSim or QuestaSim in my case. And well, all of these scripts are so let me just enable. Run this. So let's now run my simulation. So we have now completed the HDL code simulation run. We are comparing the output of my reference model with the output of my code simulation model, and as you can see, in both cases there is no difference. And at the same time I can still have a look at the output of my digital waveform. In fact, I can place breakpoints in ModelSim if I want to stop at this particular place. So this also gives me a very deep visibility in the way how the HDL code is simulated. But as you can see, it's a very easy, quick way of verifying code, whether it's correct and whether its behavior is the same as the reference model in Simulink. Now, where I have done this now in Simulink, obviously we can also perform this kind of code simulation between MATLAB and ModelSim. Okay, so let's close the model and go back to the PowerPoint presentation. So let's now have a look at best practice 4 and see whether we can reuse the system level test bench to enable regression testing with FPGA in the loop simulation. So if you look at FPGA in the loop, essentially it creates a code simulation interface with FPGA boards. In this particular case we support a range of Altera and Xilinx FPGA development boards. But the idea is that stimuli data from a test bench in Simulink, we send stimuli data through Ethernet to the FPGA board, and through that same interface we receive simulation results back, which we can further use for further analysis in Simulink. And as you can see, FPGA in the loop provides you with same kind of benefits as same kind of flexibility as what HDL code simulation gives you, in the sense of that the test bench can have closed loops, can have multi-domain components and so forth. So it provides you with a lot of flexibility in constructing your test benches. And obviously, where HDL co-simulation works with handwritten code, FPGA in the loop also works with handwritten code. This capability is actually also provided by HDL Verifier. So HDL Verifier gives you the ability to co-simulate with HDL simulators, but it also provides you with the capability of co-simulating with FPGA hardware. So let's now go to the Simulink model and see how we can further perform regression testing of our audio equalizer running on the FPGA board. Okay, so let's open up the FPGA in the loop verification model of the audio equalizer, which is this. So if you look at this model, we have the FIL block, the FPGA in the loop block, which represents our co-simulation interface to the FPGA development board. So let me just double click on this block. Download the programming file, and as you can see, in this case we have chosen for an Altera FPGA development board. One key difference between previous test benches is that we are now using actual audio data. So we have a WAV file containing some audio data, and one other important thing to notice here is also that we're not sending sample-based data to the board, but we're buffering data, so we are sending buffered data to the board, which helps me again to speed up the overall performance of this model. And when we receive the output, the left and the right audio output, we're combining this, and this goes to the two-wave device, so we actually play the output of the audio equalizer. So let me see where we are with the programming file. Okay, so that was successfully. So let's close this one. And let's run the play button. So we can now really hear the effect of the audio equalizer. So if I change to a different effect, let's say classical, we can now really hear the effect of this other audio equalizer mode, classical. And if I change it to jazz, for instance, then the audio output will sound again different. And let's go back to rock. So let's stop the simulation. So this provides let's say a way of testing the algorithm where we can really hear the effect of the audio equalizer, but also where it's possible to send in larger data sets, larger amounts of data to better test the algorithm running on the FPGA board. Okay, so if you look at this picture, then there are two important things to notice on this slide. One is these are the boards we support for FPGA in the loop, and where we have chosen the Altera DE2 board, there are a lot more boards we do support for FPGA in the loop. Now, the important thing to notice here is that part of the HDL workflow advisor is that it also facilitates a target workflow for FPGA in the loop, which means that in the end the output of this workflow is the creation of an FPGA in the loop verification model where we are comparing side by side the algorithm running on the FPGA with the algorithm running in your with the reference model in Simulink, in a similar way as we have seen before with HDL co-simulation and the validation model. So it's not just that we want to give you the capability to perform FPGA in the loop, we also want to make it easier for you to actually use these kind of capabilities by automating the process of creating these kind of verification models. This is a workflow which works together with HDL Coder. However, we also provide you with wizards to perform, to get to the same results for handwritten code. Now, one other aspect when it comes to regression testing is that at some point you may want to test it standalone, deployed standalone on an FPGA board. For instance, the algorithm is programmed on the FPGA, and where you may want to take advantage of the audio input and output of this FPGA board. Also, for that we do have a workflow to facilitate that verification step. So let's go back to Simulink and let me show you how this workflow looks like. Okay, so let's open up our model. And in this case we have extended the model from being just an algorithm level model to a model which not only contains the algorithm but also contains the driver components, in a sense that we do have an audio codec controller. We do have an interface with an LCD display to show us textually what effect we have chosen. We have a part which is responsible for choosing, for taking the input of the chosen effect. We are using the rotary encoder on the board to use that as a way to control the volume. And additionally, we have enhanced the algorithm also to perform a spectrum analysis and show that output again on the LCD display. So there are various things we have done additionally to further enhance the algorithm, but also to further add the peripheral drivers to be able to deploy this algorithm standalone on this FPGA board. And also for this workflow we are going to use the HDL Workflow Advisor. So where we have started by using the HDL Workflow Advisor to target a generic ASIC FPGA ASIC target, we have explained how you could use the FPGA in the loop workflow to generate FPGA in the loop verification models. This is an FPGA turnkey workflow, which in the end facilitates a workflow where you would be able to choose a specific target platform. And in my case I want to use now the ML506 board. So you can see that immediately the Workflow Advisor chooses the correct FPGA devices. So let's run this task. Now I've identified which board I want to use. I also know which peripheral interfaces exist on that particular board. And so the next step would be to connect the I/O of my Simulink model to the specific peripheral interfaces of my FPGA board. So let's go there. So these are all of my inputs and outputs. So let's say I have a tone input for which I want to use one of the push buttons to be able to select a specific effect. I have my serial data in for the audio codec. I have my bit clock. And you see that in this particular case for this board we have already pre-populated the required interfaces. So I have my rotary ink A, ink B, my push button, audio reset B, as data out, my sync, this is for my LCD display. Okay, so I've now connected all of my inputs and outputs, and in case something does not appear in this list, you can always specify the specific FPGA pins you want to connect that particular input or output to. But in this case all interfaces exist for this particular board. So this is the target interface configuration. Then I would be able to specify my system clock frequency. So I know my board has a 100 megahertz clock frequency, but I may want to change it to, let's say, 50 megahertz. So let's do this, which means that we are inserting a clocking module which handles this this clock conversion. So which essentially will be a DCM and for this particular board. So let me run again all steps for to prepare my model for HDL code generation. Okay, and generate HDL code. Now you may notice now that this option here is checked. So in addition to the top level of for HDL coder, we add an additional FPGA top level wrapper file, and I will show you this in a minute what this exactly is. So let's generate code, and in this case we will not only generate HDL code from this particular system, we will also generate, as I said, a wrapper file which also instantiates a clocking module which handles the clock conversion, and additionally we will also generate a user constraint file which constrains the FPGA implementation tool to connect the I/O of the Simulink model correctly to the correct FPGA pins. So let me just show you this. Okay, so we have generated the code, but the part which I want to show you is, for instance, this top level wrapper file. So this is the ultimate top level entity, but here we have our clocking module. This is our design, and this is the way how we interconnect the inputs and outputs of my design of the Simulink instance with the rest of the design. If you look at the clocking module, then this is basically instantiating a DCM which is correctly configured for converting the clock from 100 megahertz to 50 megahertz. Right. Okay. So and the last thing I'd like to show you is the UCF file which we have generated, and here we have we have linked every output to the correct pin of this particular FPGA board. So if you go to the next step, here we need to create our FPGA project, and in this particular case a part of my design of my interfaces I have explicitly modeled. For instance, I have modeled the LCD display by using MATLAB code and Stateflow, and that was a fairly easy task by using MATLAB and Stateflow. Same is true for my push button interface. Again, we have used heavily Stateflow and MATLAB code. But for my audio coder controller, I potentially could have modeled it in Simulink. However, in this particular case, I already had the corresponding HDL sources. So for that reason, I have chosen not to model this in Stateflow in Simulink. So instead, what I want to do is I simply want to make sure that those source files can be included in the whole build process. So if I go to the HDL sources, then this is basically, these are the HDL source files for my audio codec controller, and I create the FPGA project. And this will automatically insert all HDL sources, connect them correctly, and then we are ready to perform all implementation steps. So if you now look at the ISE project, then you will see that the structure in that sense is complete. Okay. So here we have our ODEC controller, for instance. And the next step would be to perform all implementation steps, generate a programming file, and program the target device by means of the JTAG interface. Okay, so to summarize this webinar, with the first best practice, we have used modeling and simulation to optimize at the system level using Simulink and Simulink fixed point. So we primarily focused on how we could reduce the word length of our fixed point data types to have more area efficient and power efficient implementations. With the second best practice, we have automatically generated readable, traceable HDL code using HDL Coder. And we also focused on how we could optimize on area and speed. With the third best practice, we have reused the system level test bench to verify the generated HDL code by using HDL Verifier, which establishes an HDL co-simulation link between Simulink and, in our case, ModelSim. And with the last best practice, we have enabled regression testing with FPGA in the loop simulation using HDL Verifier. And additionally, we also had a look at the FPGA turnkey workflow, which enabled us to fully deploy an algorithm running standalone on an FPGA board, where we could take advantage of the audio input and output peripheral interfaces of that specific board. So finally, I also would like to share this customer example with you, which is FLIR, who has been very successful using the MATLAB to HDL workflow, and as a result they were able to reduce the time from concept to field testable prototypes by 60%. They were able to complete enhancements in hours and not in weeks, and they actually are now able to have a higher level of code reuse, which was increased from 0 to 30%. And as a result of all of this, there was also much more joy in engineering work, which is also a very important aspect, I would assume, with your day-to-day work. So to conclude this webinar, please visit our website if you want to know more, if you want to have more information on HDL Coder or HDL Verifier. Please follow these links. We have also more webinars on FPGA and ASIC, so please go to our website and watch these webinars if you like. But if you feel that HDL Coder and HDL Verifier can be beneficial for your project, please contact your local sales rep and ask for a trial of our FPGA and ASIC tools.